Hi, I'm Chintu Gopal. I'm a quant researcher at Bloomberg, and today I'm going to talk about applications of deep generative modeling in finance. Within the last decade or so, deep learning and generative modeling have become amazingly popular to the point that deep learning is the de facto method to model images and text. However, even though majority of the research focuses on these rather narrow applications, the techniques can be distilled down to their underlying innovations, and it's these innovations that can actually be applied to a much larger range of problems, including those using financial data sets. So in this talk, I'm going to talk about concrete applications of deep generative modeling in resolving real-world problems in financial modeling that arise because of inherent difficulties in financial data sets. More specifically, I'm going to be talking about what is amortized inference, how it's useful to fit generative processes, and then talk about state-of-the-art deep generative models like GANs, normalizing flows, and VAEs, and how they can be used to fit complex distributions. So first, what is generative modeling? The simplest definition of what a generative model is any model from which we can sample from. So the simplest version of this is like an analytical distribution, so like a categorical or a normal distribution. And in both these cases, you have explicit densities. And from this, you can compute statistics like mean, variance, or other even information theoretic quantities. However, there are other models as well, which we can sample from, but we have no closed form density, and these are considered implicit density models. And we'll actually show how both these types of models are useful in finance. Before delving into GANs, normalizing flows, and VAEs, first I want to answer the question, what is amortized inference? To better explain the techniques, a practical example I'm going to talk about is carbon modeling. Interest in a company's carbon emissions has grown, but the problem is that majority of companies don't report this number. So the goal of this model is to estimate a company's carbon emissions from all the data we can collect for that company. The data itself is quite interesting because it's annually reported. And since this data has only been collected for a decade or so, there's maybe only about 10 observations per company. On top of that, there's no real regulation saying companies have to report this number, so maybe about 1,000 companies report their carbon emissions. So all in all, we only have about 10,000 labeled rows. And then what we want to estimate are distributional estimates, not simply point estimates of the mean. Often in finance, what we assume is that there's a distribution of possible observations per entity. So say for trade cost modeling, we assume there's a distribution of possible trade costs per security, and carbon modeling, we'll assume there's a distribution of possible carbon emissions per company per year. What this distribution will model is aleatoric uncertainty or model uncertainty. Basically, the question it should be able to answer is, for companies with these features, what is, say, the 90th percentile of possible observations? An important note here is that this distribution does not capture epistemic uncertainty or statistical uncertainty. Basically, the uncertainty that arises from only having a finite number of samples. So a theme that's going to reoccur over the next few slides is what we can do to make sure we minimize the statistical uncertainty. The traditional technique for this would be to partition/bucket the companies into similar subsets and then fit a linear model in each subset. The simplest way to bucket the data would be to put all the observations of a single company in a bucket. The problem is that you wouldn't have enough data because the data is only reported annually. In the optimal scenario, right, we would have infinite amount of data per company, and then we could just fit a distribution. But in the practical scenario, what we really need to do is somehow get distributional estimates from only a finite number of samples. So what we could do is expand our definition of similarity to incorporate companies from the same industry. And in this way, it could share the statistical strength, reduce statistical uncertainty, while possibly increasing the bias of the model. So the linear model we want to fit is a gamma generalized linear model or a gamma GLM. We could just fit a regular linear regression model and then take the statistical view of it being a conditional normal. But since carbon emissions is always positive, you would rather fit a gamma, hence a gamma GLM. An implicit assumption in this technique is that every bucket is independent of every bucket. By this, I mean, by utilizing this technique, you're basically saying that data that exists in one bucket would not inform the model in another bucket. Or in other words, the data in one bucket would not reduce the statistical uncertainty of the model in another bucket. On top of this, there's a few problems with this bucketing approach. Within one industry, there will be companies from different countries, that have different sizes. And we would like to be able to account for this information too, but if we try to bucket on all this information, we'll fall back to that scenario where we don't have enough data. On top of this, there are notions of similar industries. And this actually breaks our implicit assumption because that means there's data in one bucket, which will be useful for a model in another bucket. And this is kind of what the troubles are with bucketing. You're trying to come up with a scheme that is meaningful as well as effective in terms of having enough data. So the amortized inference approach is to train one model on all the data. So what the model is you have features that go into some model and it will output k in theta. And really it's a design choice if you want to have two models, one for k, one for theta, or just one with multiple outputs. But the main point here is that you're modeling a full distribution. And so in this way, you're actually going to also be able to handle heteroscedastic data. So the majority of the research that exists for regression often uses mean squared error or mean absolute error, but these are only going to give you the mean or the median. So instead of trying to just match the mean, since we want distributional estimates, what we would rather use is maximum likelihood estimation. Or in other words, the loss will be the log likelihood, and then we could optimize our model using gradients. So at high level, what the models become is features, model, differentiable log likelihood loss. So the choice of the model is actually kind of arbitrary. It just has to be any model we can optimize via gradients, such as neural networks or linear models. Though you could really just say linear models are a special case of neural networks. And so the choice of model doesn't matter. What really matters in amortized inference is the fact that you're training one model on all of the data and you're outputting a full distribution conditioned on features. But why would we want to use, say, a neural network? One is because each company has hundreds of features, and ideally we would like to utilize all the information that we have. On top of that, a linear relationship is not necessarily justified for all our features. This is often the argument people make of why to use a neural net. Let's just take all the data and throw it at it and hope it learns. But really, there are clear-cut benefits of using amortized inference. One benefit is that you can share the statistical strength across all your data. Majority of financial data sets are scattered. And by this, I mean, like in carbon modeling, there will be industries with a lot of data, and there'll be industries with very little data. And the industries with very little data will have very large statistical uncertainty. But if you train a model on all of it, then the model can see observations of similar companies, not just companies of the same industry, and be able to learn something useful from that. The other reason amortized inference is useful is that really it's kind of implicitly bucketing the data for you. So in terms of neural networks, one view of neural nets is that it's creating a representation of your data, and that representation gives you a similarity metric on the rows of your data set. And so if you take the representation, i.e. the output of a hidden layer for one company, and take the representation for another company, take their dot product, this is going to define a kernel. And so one way to use neural networks is that it's trying to learn a kernel that best works for the target task. And really bucketing in essence is doing the same thing. If you have data in different buckets, the similarity is 0. And if you're in the same bucket and using a linear model, the kernel is simply the dot product of their features. But this throws away a lot of information about other features. And so really you can think of a neural network as a generalization of the bucketing approach. And then another reason amortized inference is useful is that it kind of makes it easy to see how you could fit more complex distributions like multivariate distributions. So for example, carbon emissions are often given in multiple fields. And so you can think of those as direct and indirect carbon emissions. If you want to model both, let's just update our generative process. Direct carbon emissions will come from one gamma distribution, and indirect will come from another gamma distribution. Then we will update our amortized inference model. So now it becomes features, model, 4 outputs. And these 4 outputs will parameterize our 2 gamma distributions. And then our loss will just be the log likelihood of both, added up, optimize. And again, diagrammatically, I put neural network, but it doesn't have to be a neural net. Just any model you can optimize via gradients. And by using one model to handle both targets, you're going to be able to learn better representations of the data. And more interestingly, If we assume direct and indirect carbon emissions are conditionally dependent given the features, we can incorporate a learnable correlation term. And then if we have indirect carbon emissions, this will actually inform the direct carbon emissions model and reduce the statistical uncertainty. Another useful example for amortized inference is trade cost modeling, where we define trade cost this way, as the percentage difference between the trade price and the true/fair price of a security. The interesting point about this data is that less than 1% of securities have more than 5 trades. So whereas carbon modeling was scattered with respect to industry, this is scattered with respect to securities. And then, similar to carbon estimates, we want distributional estimates per security. So here we see the results for baseline model, bucketing approaches, and amortized inference. Along the x-axis, we have the different models we're comparing. Inside the plot, the different colors represent the performance on different subsets of the data. We define the different subsets by the volume traded because there's very few trades with large volumes and many, many more trades with small volume. And then along the y-axis, we have the relative RMSE. This is just the RMSE of the model divided by the RMSE of the baseline. And we want this number to be ideally less than or equal to 1 and try being as small as possible. So the first example is the baseline model. Since it's the baseline model, the relative RMSE is just 1. All but the last example are bucketing approaches. And so what we bucket by is by security. And then we fit a linear model if there's sufficient data, where sufficient data here is defined by having at least 10 trades. So the question then becomes is how do we predict on securities where we had less than 10 trades? And that's what these different bucketing approaches are. The first one is just saying, let's just pick a random fit linear model and see how that performs. The second one takes the average of the model coefficients for all the fit linear models and sees how that performs. The issuer one is a generalization of the average case, where instead of taking the average across the full universe, you take the average at an issuer level. And then the random forest is a little bit more complicated, but you can think of it as a further generalization of the issuer version. So the model is bucket the data, fit a linear model, and then train a random forest to map from features of a security to the fit model coefficients. And then during test time, you take a security, take its features, put it through the random forest, get the model coefficients, and from the model coefficients, get the distributional estimates. And then the last column is amortized inference using a neural network. So the first thing you can see here is that the pink line, which is for large volume trades, the bucketing approach does worse than the baseline model. And this has to do with the fact that there isn't a lot of data in this regime. Whereas the amortized inference approach is able to do just as well as the baseline model because it trained on all the data. So there's statistical sharing across the full data set. But furthermore, interestingly, that even for low volume trades, it actually does much better. And this has to do with the fact that amortized inference doesn't have to throw away any data. If you think back, with the bucketing approach, you could only train on securities that had at least 10 trades. So if there's a security with 9 trades, there's a lot of information there, but it's not being used by the bucketing approach. And so that's another cool thing about amortized inference, is that we can now train it on securities that have at least 10 trades and on securities that have even only 1 trade. So one of the reasons we often don't want to use neural networks in finance is a lack of interpretability. However, there's actually a way to add interpretability to amortized inference. And we can do this by asking ourselves the question, do we have any known relationships between the features and the target? So for example, let's say we want to assume that carbon emissions is linearly proportional to company size, right? And what this means is basically saying that all else held constant, if we increase the company size, carbon emissions should go up as well. We could try checking if the neural net has this encoded, and check it on every company we have, but there's really no easy way to ensure that this property holds true globally. So what we can do instead is update our generative process. So instead of having 2 parameters, k and theta, the generative process now has 3 parameters, a bias term A, a slope between the company size and carbon emissions B, and theta. So now instead of giving company size into the neural network, it stays just at the generative process. And actually, this example pushes the relationship between amortized inference and bucketing even closer. Whereas the bucketing approach would have a different set of A, B, and theta per bucket, and then have some dictionary that maps from bucket to these parameters, the amortized inference is a more continuous version of it, where it's a function going from features to A, B, and theta. And even if the only additional feature we had was industry sector, this is still useful because you could then put industry sector in the amortized inference model and then train the whole model end to end. So this is really useful anywhere we actually know something very specific about our data. And then whatever features we know, we'll put that in the generative process, and for the rest, they'll go into the neural network. And so the example I showed is what happens if they're linearly proportional. But what if you want to make a less strong assumption and say it's sublinear? So we can easily do this. We just add another parameter c, raise company size to that power, and then make sure that c is between 0 and 1 by using a sigmoid function. And so really, I think the best way to think of amortized inference is as a continuous version of the bucketing approach, taking a more data-driven approach to learning the bucketing mechanism instead of trying to design the distance metric by hand. So for the rest of the talk, I'm going to talk about state-of-the-art deep generative models and how they can actually help fit complex distributions. So one limitation we have with MLE is that it requires an explicit likelihood. So many distributions are sums or mixtures of random variables, but if it's too complex, it can be hard to compute the likelihood in closed form. However, when we define generative processes, often the way we define it is as a sampling process from which we get the observations. So the question comes, can we fit the parameters of a distribution from which we can only sample? That's what likelihood-free estimation is, and the answer is yes, we can do it, and we could use GANs. So what are GANs? The best analogy for GANs is to think of the generator as a counterfeiter and the discriminator as like a store clerk trying to figure out, is it real or fake money? So if the store clerk gets tricked by the counterfeiter, then it's going to learn how it got tricked and get better. And then if the discriminator, i.e. the store clerk, is able to catch the counterfeiter, then the counterfeiter learns how it got tricked and gets better accordingly. And this is the adversarial game they're going to play against each other. Mathematically, it's a minimax game. The discriminator is trying to maximize its classification accuracy for determining real or fake samples, and the generator is trying to decrease the classification accuracy by creating more and more realistic samples. And effectively what this does, it minimizes the JS divergence. So yes, MLE is minimizing the forward KL, but if there's no real model misspecification, optimally, they both will converge to the same solution. So though most of the research for GANs is trying to just kind of create highly realistic images, really distilled down to what it is, it's a way to do likelihood-free estimation. So an example for this, where it's useful, is trade cost estimation. So we actually have a very interesting data set where we don't know the trade direction. So the data set contains trades from dealer to dealer, dealer to client, and client to dealer, but we don't know which is which. And so what we want to estimate is the mixture of these three components. So first thing we need to estimate is their mixture rates. We don't know what proportions dealer to dealer or dealer to client or client to dealer. And so we need to learn these. And then we need to kind of decide what distributions we want to put in each individual component. So for the dealer to dealer, we assume they don't want to charge each other. So we model that with the normal distribution with zero mean. For dealer to client, we call that a buy trade because it's a buy from the client's perspective. So if you imagine you're a client and you're buying from a dealer, you know the dealer is going to charge you more than the fair price. So that means the trade cost will be positive. Hence, we model that with the log normal. For client to dealer, we call that a sell, and using the opposite argument is going to be a negative log normal. But one additional component on top of all this is the market risk component, and we model that with the normal distribution with zero mean. So here we see an adversarial loss trying to fit this distribution. The solid histograms are samples from the true distribution, and the dashed histograms are samples from the learned distribution. And so an important note here is that the model, and even in reality, all we have access to is the yellow histograms. So the adversarial loss is just trying to match the two yellow histograms. The red, green, and blue one are shown here, but that's just to show where the mixture components come from, not because we actually have direct access to it. But what's cool is that as the adversarial loss matches the yellow histograms, it's actually matching the individual components, not just the parameters in them, but also their mixture probabilities. And so basically what we did, instead of using a neural net in the generator, we replaced it with an analytical generator. And we still use a neural net in the discriminator. And actually what we did in practice is we replaced the generator further and used an amortized inference approach that maps security features to the parameters of this mixture distribution. So interesting observation here is that even though the discriminator is a neural network, it doesn't actually control the capacity of the generator. In other words, even if I increase the capacity of the discriminator, that won't increase the overall complexity of the generator. The discriminator is simply there to help optimize the generator. Or in one more set of words, with the generator, the family of distributions it can describe is predefined from the beginning. The discriminator is simply trying to find the best one of those that best fits the data, and the capacity of the discriminator controls how well it's able to do its job. And so really the cool thing we've seen here now is that now we actually have a way to fit distributions where we know the generative process, but we didn't have to compute a single closed form likelihood. So another state-of-the-art generative model is normalizing flows. Another limitation with this overall technique is the choice and flexibility of the output distribution. So for example, assume the data is bimodal and we fit a normal distribution to it. What's going to happen is that you're going to get a mode averaging effect. The normal distribution is going to be wide enough to cover both modes. And in the plot, you can see that the percentile distribution really don't well capture the actual data. And so if we have no theoretical assumptions for our distribution, we should really be allowed to use any freeform distribution that we want. And there are ways to handle skew and heavy tails using like student's T, but what we're going to do is take a deep learning approach to learning complex distributions. And one way to do this is using normalizing flows. What are normalizing flows? Normalizing flows are a technique for density estimation. The goal is to take the input distribution, like this mixture of Gaussians, and transform it to a base distribution, like a normal distribution, using an invertible function. And then you can sample from this by sampling from base distribution and applying the inverse of this function. The likelihood can then be computed using the change of variables formula. So the computation required here now is applying the invertible function, computing the log likelihood with respect to the base distribution, and computing this rather complex log determinant of the Jacobian term. So from normalizing flow research, there are actually now functions now that are parameterized by neural networks that are invertible and where you can compute this log determinant term rather simply. So the main thing to know here is that this function f, it's different from the function in amortized inference because this function controls the shape of the distribution. So even if you don't condition on any data, it can learn complicated distributions like this mixture of Gaussians. And actually this example here is what's learned by an example of normalizing flows called core flows, which is a new type of normalizing flow recently published this year by me at an ICML workshop. So the power of normalizing flows comes from the fact that it can fit really complicated distributions that would be very hard to describe analytically. So what we see here are contours of the likelihood learned by normalizing flow on simulated data. So say in practice, we saw this first plot and we saw the data look like this. It'd be rather kind of obvious to say, okay, let's fit a mixture. But if we're to see the second pinwheel distribution, really this is almost impossible to describe that analytically. But in both scenarios, a normalizing flow is able to fit it. And actually the first example is interesting as well because the normalizing flow doesn't know a priori how many clusters there are. All it's trying to learn is how to map from a 2D normal to this mixture of 8. Similar with the pinwheel, it's just trying to learn how to map from a 2D normal to this pinwheel shape. So you could argue, right? You're not going to see something as interestingly weird as this pinwheel distribution, but at the same time, you're never going to see anything as clean as this mixture of Gaussian. But in both scenarios, the normalizing flow is able to fit both utilizing the exact same model architecture. So now if you want to use flows with other features, the model becomes this. The features go into a neural network, the neural network outputs a representation, and then the flow will be conditioned on that representation. And since the flow is just a distribution, ideally what we want is that when you condition on the representation, it best fits the target. And actually we could merge this with amortized inference, imagining the neural net as a hypernetwork, and it outputs the parameters of the flow. So again, the benefit here is that it's a more data-driven approach to learning the distribution. It learns the shape from observations, not simply from external knowledge. But really the main benefit, I would argue, is when you're trying to model multiple targets that you know are correlated with each other. Modeling complex one-dimensional distributions is a thing many people have done, but trying to model high-dimensional distributions can get really complicated. Copulars are one way to handle this, where you can define the correlation structure, but even utilizing external knowledge to design that function can be really hard. And it can become near impossible if the targets have different types. Like say some subset are real valued, some are binary, some are categorical. Trying to design that becomes extremely difficult. But the flow can handle this, and it can learn the correlations from the data. And we know it's able to do this because majority of flow research is using it on images. And images are really just an amazing example of super high dimensional data with very correlated dimensions. And so comparing this use case to the GAN, I would almost argue they're kind of opposite in the use cases. GANs are really useful when you have very specific theoretical justifications for a distribution and you need to make sure you fit that. Where on the other hand, if you really have none and you don't even care about the shape of the distribution, flows are really useful for that. So the last deep generative model I'm going to talk about are variational autoencoders, or VAEs for short. So one way to optimize statistical models is to use variational inference. And variational inference is actually solving a similar problem that GANs are solving. And so imagine you have a generative process with some latent variable that you can't efficiently integrate away. So what variational inference is trying to do is basically approximate the posterior to help perform MLE. So the traditional technique is to approximate the posterior for all your data points and then maximize the likelihood given the posterior. So a simple example of this is a mixture of Gaussians. The generative process here is we sample a category Z from a categorical distribution parameterized by pi, and then we sample the observed variable X from a normal distribution indexed by Z. So Z here is the latent variable, the prior is the categorical, and the likelihood is the normal. We then approximate the posterior with another categorical distribution conditioned on the observed data. And so what this is trying to answer is the question, given the K clusters, what's the probability that a certain data point came from a specific cluster? So mathematically what we do is we're going to maximize the evidence lower bound, or ELBA. And in the right side of this equation here, Q is the approximate posterior and P is the generative process. So what you would do is you would plug in the definition of all your distributions, expand it out, and then maximize it with respect to Q, then with respect to the parameters in P, and then you alternate until convergence. More specifically, you would replace Q here with the categorical distribution parameterized by theta, replace P of Z with the categorical parameterized by pi, and replace P of X given Z with the normal distributions. And so if you have a more complex generative process, doing this math by hand can get rather hairy. And so the innovation of VAEs is to optimize the ELBA by replacing the closed form computation of theta with the neural network instead. And so this is what it becomes diagrammatically. So you have a data point, it'll go into a neural network, the neural network will output theta, and theta parameterizes the categorical distribution. And as you can see, this is just another amortized inference model. You have some feature, and it outputs parameters of a distribution. And so then you sample a category Z from the categorical. And just doing this, you can estimate the ELBA. To the right, you have the probability of the category given pi, the probability of the category given the distribution from the neural network, and then the likelihood for the observed data is the likelihood of X given the normal distribution indexed by Z. And now we can compute this on a batch of data, compute the gradients, and then optimize all the parameters in the neural net, pi, and the normal distributions. And that's all a VAE is. It's a way to combine amortized inference, neural networks, and gradient-based optimization for variational inference. So the question comes, where's the autoencoder? So what is an autoencoder first? An autoencoder takes some data point X, sends it through an encoder, which embeds the data, and the embedding goes into some decoder, and the output of the decoder is trying to reconstruct X using some loss like an MSE. And really, that's what this diagram actually is showing. So the neural net here is the encoder, or in the amortized inference network, it's called the inference network. So X gets encoded into theta, and then the generative process decodes the data. And so if you expand out the log likelihood with respect to a normal distribution, what you get is an MSE loss plus a term on the variance. And so that's where the autoencoder is. We got the encoder, we have a decoder, and we have a reconstruction loss. And the other two terms you can kind of think of as regularizations on the embedding space. And that's where the name autoencoder comes from. But really what a VAE is that it's just simply variational inference. So similar to how I said earlier, right, that variational inference is useful to solve the same problems as GANs, this is how you would use it if you're trying to optimize the directionless cost model. Diagrammatically, it looks rather complex, so I'm going to break it down. So this part is just a mixture of the dealer to dealer, dealer to client, and client to dealer part. So if this were the only part of our model, it's just going to be similar to the mixture of Gaussians. We would just approximate the posterior of Z. But we have this additional complexity for the market risk component that we add in. So we're going to approximate the posterior of this component too. And the reason we do this is if you think about it this way, if we had a value for market risk, then trade cost minus market risk would give you X. And then you're just back into the normal mixture case that we already know how to handle. So for variational inference, we basically tacked on this neural network. The neural network outputs theta for approximating the posterior of Z, and then a normal distribution with mu and sigma for the posterior of market risk. An important note here is that the distribution of market risk given trade cost is not necessarily normal. And that's why I've been using this phrasing, approximate posterior. And so the likelihood can be computed this way now. Trade cost goes into the neural net, you get a normal distribution, sample market risk from that, subtract market risk from the observed trade cost to get X, sample Z from the categorical parameterized by theta, and compute the log likelihood of X given the cluster that Z indexes into. So compared to the GAN approach, this is definitely a lot more complex, but this is a way to merge a traditional technique with deep learning. And so one of the main benefits of using this is that it's going to use less memory than the traditional technique. So instead of having to compute the posterior for all your data points and keep that in memory, you can do this only on a batch of data, and the neural network will eventually efficiently learn what the actual function is. And so if you imagine a neural net as really just a fancy dictionary, you can be certain that eventually you'll learn the correct function. But really one of the main benefits of using this framework is you can utilize other VAE research. And a lot of that research is to tighten the bound of the L-bound. So the tightness of that bound controls how well estimated your parameters are. So if the bound is too loose, you can't even be sure you're optimizing the right function. So if you take your variational inference problem and convert it into the VAE framework, you can then utilize these benefits like importance-weighted autoencoders to tighten that bound and improve the estimates of your parameters. On top of that, a few months ago, there was a paper that showed you can actually optimize VAEs with an unbiased estimator. So what does that mean? There's now an unbiased estimator for variational inference, and you wouldn't be able to utilize this unless you think about how to merge all these things together. And then another observation, very similar to the GAN, is that the neural network here doesn't control the capacity of the generator. Family distributions are predefined from the beginning, and the neural network is simply there to help optimize that generative process. So you can't actually put millions and millions of parameters into the neural network, and that won't change the family of functions or the capacity of your generator. So in summary, really, the best way to view amortized inference is that it's a lens to view how deep learning can be applied to generative processes. And really, you could argue that all of deep learning is amortized inference. Let's look at a classification model. A classification model takes some input like an image and maps it to the parameters of a categorical distribution. Further, we can combine financial generative modeling with deep generative modeling by distilling down deep learning research to its underlying innovations. So for example, GANs. GANs are introduced as a way to create highly realistic images, and up until recently was the state-of-the-art method to do this. But distilled down, what it really is a likelihood-free optimization process. Normalizing flows are often used for density estimation of images and more recently on manifolds, but distilled down is just a way to learn complex distributions. And then VAEs, similar to GANs, were introduced as a way to optimize the generative process for images. But distilled down, it's just a way to combine variational inference with deep learning and gradient-based optimization. And so there are other examples of the same idea, and so I'm going to leave this as a final note. For ML in finance, really our job is not to just take the research that exists and directly apply it to our data. What we need to do is look at the research and figure out what the intent of the technique is, and then translate that on into our domain. Thanks for watching my presentation. If you have any questions, forward them on to the organizers and I'll answer them later. Thanks.